Okay, let's work this elastic collision problem. And in this problem, we have a ball of mass, we'll call it ball 1, of mass 0.7 kilograms. It's moving at 5 meters per second, strikes a stationary ball 2 of mass 3 kilograms. And we want to know, in the final situation, after that collision, what's the final velocity of ball 1 and the final velocity of ball 2. Okay, so this is an elastic, well, it's a collision, first of all, so momentum has to be conserved. So our equation then for momentum conservation, so for momentum, our initial momentum here has to equal our final momentum. So our initial momentum, well, this guy has 0 momentum. So our initial momentum is just the momentum of this ball. Momentum, again, is mass times velocity. So the mass is 0.7 kilograms. Velocity is 5 meters per second. And I'm just going to drop the units here because it's really kind of cumbersome dealing with units. Just as long as we know they're in the right units, kilograms and meters per second, we're fine. And that equals the final momentum, which is mass of this ball times its velocity plus mass of that ball times its velocity. And we know what M2 and M1 are. M1 is 0.7. Okay? And M2 is 3. So we'll just put those in there right now. Okay, so there's one equation, but we have 2 unknowns. So we can't really solve it with just momentum conservation. But the other thing that's true about elastic collisions is that kinetic energy is conserved. Okay, kinetic energy is 1/2 mv squared. This guy has 0 kinetic energy because he's at rest. This one has kinetic energy, which is 1/2 its mass, 0.7, times its velocity squared. Okay? So that's the system's initial kinetic energy. That has to equal the final kinetic energy, which is 1/2 mass of this guy times its velocity squared, which is 1/2 times 0.7 v1 squared, plus kinetic energy of this guy, which is 1/2 times its mass, which is 3, times its velocity squared. Okay? So there is the setup. We have 2 equations, 2 unknowns. Let's multiply some of this stuff out. 0.7 times 5 is 3.5. So we have 3.5 here. Okay. 1/2 times 0.7 times 5 squared is 8.75. One half times 0.7 is 0.35. And 1/2 times 3 is 1.5. Okay. So, 2 equations, 2 unknowns. And I think, you can tell right away these can be kind of messy algebraically. So I think the best way to do this is to first solve this equation for one of these variables. And I solved it for v1. So what you get from the first equation there is v1 equals 5 minus 4.286 v2. Okay? Now we take this, plug it into the second equation. And when you do that, you get the following. You get 8.75 equals 0.35 times this, 5 minus 4.286 V2, all of that squared, plus our 1.5 V2 squared. Okay? So again, still messy, but this is relatively easy to solve for V2. So we now have just V2 involved in this equation. So you do the algebra, multiply stuff out, and it's not trivial. It involves several algebra steps, just a little bit messy. It's important to keep track of your numbers when you do this. And the number I got for V2 was 1.89 meters per second. Okay? Now, to find V1, we take this and plug it back into this equation. So 1.89 goes in here for V2. So 5 minus 4.286 times 1.89 gives you V1, which is negative 3.11 meters per second. Okay, so there's our solution. What really is going on here then in this collision is that V2, ball 2, does in fact move this way, okay, at this 1.89 meter per second value. But V1 bounces back. And so V1 is moving this way at 3.11 meters per second. Okay? So again, these can be very algebraically messy, and I really skipped a bunch of steps here just to get to the answer and not kind of clutter things too much. But fortunately, the textbook has worked this out in a general case, and so there are a couple equations in the textbook for just this type of situation, given an arbitrary M1, arbitrary M2, and whatever V1 initial. And it tells you what V1 final is and V2 final are. And that particular equation is going to come in handy in a couple of the homework problems this week, at least one of the homework problems. So anyway, I just wanted to work through to show that it is kind of somewhat messy to do this. But you can see the concepts applied: conservation of momentum, conservation of kinetic energy.